Hey, we've got Ashley turned in. Good deal. I'm always amazed when this thing works. But Ashley, it's just you and me right now. And we're going to do dynamics. It's November 23rd. It's a little short week this week because of Thanksgiving. Hey, Stuart is with us. Yay. Excellent. Let's see who else we got here. And it's just Ashley and Stuart. That's so far, so good. Any questions before we begin? Hey, we're going to start here in about 1 minute. Any questions? Well, I wonder if you guys can hear me. If you can hear me, if I'm unmuted. And Shane's here. Stuart, Shane, and Ashley so far. Braxton's here. Unmute and tell me if you can hear me okay. Somebody.
Yeah, I can hear you.
Sounds like you can hear me okay. Good. Excellent. Well, unless you have a question that you want, I'll just start doing stuff that I want. Your final is the 7th of December. I've got a calendar here. Now today is the 23rd. Next Monday is the 30th. It's the last week of school. And then the following Monday is the 7th. So 2 weeks from today, your final will be available. And it'll be due on that Thursday. It's a take-home final. You'll do great. But what are we going to do today? Let me think about this. I thought we could do a review problem 19.3, unless there was something that you wanted me to do. Well, okay. We've got Stuart, Shane, Braxton, and Ashley so far. Got a good class. So let's do a review problem 19.3. It's on page, don't know. Let me find it here. It's on page 558. It's a, looks like an automobile tire rolling down the hill. Okay. Well, let's draw a 30-degree hill here, shall we? I'm actually going to measure this. I've got a protractor here. I'm going to measure 30 degrees. Here we go. 10, 20, 30. Put you right there. Right, right. 10, 20, 30. Yeah. Okay, we've got a 30-degree hill there. And we have an automobile tire. All right, well, here, I'll draw it. There's your automobile tire. It has a radius of 0.3. meters. But the radius of gyration is 0.225. So let's get the moment of inertia on this thing. It's 9 kilograms, 0.225 meters squared. Okay. All right. Let's see what that is. Well, I got an answer. Let's just check on my friend. How come I can never read the stuff at the very bottom of this dang thing? It's kind of irritating. I don't know who that wonderful student is at the very bottom. Oh, well, we'll pick on Stuart. He's next to the bottom on my list. Stuart, what'd you get for the moment of inertia about the center?
I got 0.4556 kilogram meters squared.
That's what I got. Good going, Stuart. So we got that. Now, this thing is rolling. If you read it, it's rolling, and it's rolling about, we'll call it point A. So now we're going to get the moment of inertia about point A. See, that's the ICZV. Go ahead and get it. I'll get it, and then you get it. We'll compare notes. Go for it. If you just tuned in, we're doing review problem 19.3. It's on page 558. And I just got the moment of inertia about that point A. It's rolling about point A. Shane, unmute and say hello to me, please, Shane.
Good morning.
Shane, do you have that moment of inertia about that point A?
I got 1.2556 kilogram meter squared.
How come I got a different answer? Now, you might be right, Shane. Just a minute now, but that, I got a different answer. Shane, do it again. You got to go IG, and then you have to go 9 kilograms, and then you have to go 0.3 squared. Shane, do it again. I don't think you got the right number.
Yeah, I got the same 1.2556. Typing something wrong.
Well, did you add this to it? You have to add that to it, right?
Yeah.
Let me do it again. Maybe you're right. If you're right, I will humbly apologize. Now, what did you get again?
1.2556.
No, that's not what I get. I get 1.26565.
I just rounded off an IG too early.
Oh, that's not that serious. You just rounded off, right?
Yeah.
Yeah, we're okay. It's not the end of the world. It's not the end of the world. All right. Well, we're doing great. Now, what they want to know is they want to know how fast it's going after it's released for 3 seconds. They give you the time. They say the time is 3 seconds. Now, I told you guys, if they give you the time, the best way to do it is with impulse momentum. Remember, we have 4 methods that we use in this class. And impulse momentum is our, well, actually, that's what this chapter is. This chapter 19 is the 4th method. Now, if they give you the distance, see, they didn't give you the distance that it rolls down the hill. It rolls down the hill. They didn't give you the distance. But if they did, then which method do you use? Let me ask and see if anybody listened to me when I told you this. Mark, I told the students, if they give you the distance, you're supposed to use a different method. Which method is that, Mark? There's 4 methods. One of the methods is impulse momentum method. If they give you the time, then that's the method you ought to use. But if they give, Mark, unmute and say hi. Uh-oh, coffee break. All right, well, let's go to my friend Braxton. Unmute and say hi, Braxton.
Hello.
Hey, Braxton, which method do you use if they give you the distance?
I believe it's work energy.
That's it. You use the work energy method. There are 4 methods, but when they give you the time, you should use the impulse momentum method. So let's do it. Here goes. Well, there's actually 2 equations. One of them goes like this. Now what this is called is the linear impulse momentum equation. Now what this one is called, well, here, I'll ask you. Ashley. Ashley, you're a good sport. Unmute and say hi, please.
Hello.
Ashley, this equation here is called the linear impulse momentum equation. Ashley, this equation here, what's the name of it?
Angular impulse, angular
That,
momentum.
that's it. She's got it. This is called angular impulse, angular momentum. That's the angular impulse, angular momentum equation. Well, we could use both of them. That'd be all right. And why don't let's do this one here. Do I have room there? Yeah, I got some room. Okay, now what we're going to do, since it's rolling, we can do these about point A. Now, the moment acting on this tire wheel here about A is, well, you know what moments are? Moments are R cross F. You guys know that. Well, see the R there, there's the R, see it? Yeah, there it is, there's the R. It's 0.3 meters. And then the F, oh, no, wait a minute. You know what I forgot, guys? I didn't put my red stuff on there. You can't get forces without the red stuff. So let's put them on there. Now there's your mg. Let's figure out what that is. Well, it's 9 kilograms times 9.81. I can do that. That's 88. I like writing in black better. Just a minute. That's 88.29 newtons. But see, there's other red things here. We got a normal force here, and a frictional force. I'm thinking the friction's going this way. Well, I think that's it. I don't know of any other forces on that wheel. Now let's go ahead and get that normal force just for fun. That's going to be 76.46. That's going to be 76.46 newtons. Do I need to explain that? Just say yes, anybody, and I'll go through it. Anybody need help getting that normal force acting there, 76.46? Okay, I guess you got it. Don't be afraid to speak up. All right. Now back to the some of the moments about A. Well, you see, these two red forces here, they don't give you a moment. They go through A. Have I ever told you that if a force goes through a point, it can't give you a moment about that point? If a force goes through a point, it doesn't give you any kind of twist about that point. It just pushes on the point, that's all. But this one does. In that moment, it will be 0.3 meters times 88.29 newtons times the sine of 30. Now, if you don't understand that, just speak up. Now what that is a clockwise moment. No. It's counterclockwise. And what that's going to equal is, wait a minute, Auga, I forgot my time. I have to multiply by 3 seconds. Now this was 0. It started at rest, so we don't need that. But this here is 1.265 blah 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 kilogram meters squared times omega. Well, that's it. Plug that in and let's get our omega. Go for it. I'll wait. Okay, I wonder if my friend. Hey, Mark, are you back on board? Can you hear me? Say uh-huh if you can hear me. Mark. Uh-oh, coffee break. Shane, unmute and say hi, please, Shane.
Hey.
Yeah, hey, Shane, did you get this omega? Did you get this angular velocity of that automobile tire?
I got 31.392 rats per second.
Good going, Shane. $39.392 radians per second. All right, well, let's see how we did. Go to the back of the book, and we're going to see what the answer is. Now, wait a minute. Is that what they wanted? No. They want the speed. Well, see, we can get that. The velocity is equal to r omega. And the r is 0.3. So it's 0.3 times omega. Multiply that and let's get the velocity for them. I'm getting 9.4176 meters a second for the velocity. Let's see what they got. This was R19.3. Somewhere in the back, they have answers to this stuff. And what they said in the back, well, they didn't get what we got. Must have done something. Must have done something wrong here. No, that's what they got. The book, here's what the book got. The book got 9.42 meters a second. Yay, we did great. They just rounded off. They did it right, and we did it right. Do you have any questions about review problem 19.3?
I'm not getting the same omega.
Okay, hang on. To get that omega, you got to use, who am I talking to?
This is Stuart.
Stuart, I want you to take 0.3 times 88.29 times the sine of 30 times 3. And then divide it by
Okay, I wasn't multiplying by the 0.3.
I probably stuck that too far over, but you're okay. See, that's the R in R cross F. You understand? Is it Stuart? Am I talking to Stuart?
Yes.
Stuart, do you remember this R cross F is equal to RF sine of theta. Does that ring any bells? R cross F is RF sine theta.
Yes.
You remember that? Good going. See, that's how come you have to have sine of 30. Because here's the R and here's the F. Now there's an angle between them of 30 degrees. See that 30-degree angle between the F, that's the F, and here's the R. The R is actually going from A to G. But the angle between the F and the R, see, that's what this angle is. It's the angle between the R and the F. Okay, great. Any questions from anybody about review problem 19.3? Well, let's find what the friction is. See, we got the normal and we got the weight, but we never got the friction. Look, we never got the friction. I wonder how we would do that. Well, we have 4 tools in this class. And you know what the 4 tools are. There's kinematics, Newton's second law, work energy, and impulse momentum. Those are the 4 tools. I bet we could get that friction from using one of the tools. Let me ask somebody which tool they would suggest. There's more than one correct answer. I'm still bugged by this. Here we go. Taylor, it's Taylor that I want. Taylor, can you unmute and say hi, please?
Hi.
Taylor, if you were going to try to find this friction, we've got 4 methods that we use in this course. Which method would you use?
That is an excellent question.
That's the way I wiggle out of stuff that I don't know. I say, oh, that's a good question.
I don't remember the name off the top of my head. I'm sorry.
Okay, I'll give you a hint. It has initials of
Would that be Newton's second law?
that would be Newton's second law. I bet you could get it with Newton's second law. See, if they give you the time, you use impulse momentum method. If they give you the distance, you use the work energy method. Well, what if they don't give you the time and they don't give you the distance? You're trying to find the force. Well, you could use Newton's second law. Taylor, what do you think?
That sounds great.
Let's do it. Okay. Well, here, let me write it. I just need some room here someplace. We're going to have to make some room. We got the velocity. We got the omega. I don't need any of this jazz. I could erase all of this. Yeah. I think or I could ask you guys. You're taking excellent notes. If I need a number, you've all got it there. Now what we're going to do is we're going to write Newton's second law. And I think the way I would do it would be going down the hill here. I would just say that's my positive x-axis, you know. You can make your x-axis anywhere you want. It's your problem. So I'm going to go that way with it. And let's see. this has a component going down the hill. It's what we're doing is we're taking the sum of all the forces. I'm going to call that my x direction. And the sum of all the forces in the x direction is 88.29 newtons times the sine of 30 degrees. But see, you have to subtract the friction because it's not going down the hill, it's going up the hill, equals the mass, 9 kilograms times acceleration. Well, here's my problem. We don't know the acceleration. You know what? If we knew the acceleration, we could solve for the friction. But we have kinematic equations. Remember, there's 4 tools that we use in this class. The first tool that we learned was the kinematic equations. And there's one that goes like this. I bet you remember that. See, v sub 0 that's the initial velocity, that's 0. You don't even need that. And the velocity, when it rolls down the hill, we got that. It's 9.4176 meters per, we got that. And the time, that's 3 seconds. We got that. Hey, look, we could find the acceleration, couldn't we? Yeah, using kinematics. And then we could, hey, look here, we could plug in that acceleration and we could find the friction. Now I'm going to shut up for a minute and a half. I want you to find the friction. Go for it. You can do it. Find the friction. Auga. My little buddy here?
Yep.
How's he doing?
He's thrown up 5 times.
But not in your car?
No.
Oh, gee. You going to take him to the doctor or is she?
I'm meeting her there.
Ah. Okay, students, I got what I think the friction is. Let me call on one of my excellent students. Let's see here. Why don't we start with Ashley? Ashley, unmute and tell me what the friction is.
I got 15.8922 newtons.
How come I got 15.885 newtons? Did one of us round off something, Ashley?
Probably.
Yeah. What'd you get? 15.89 something?
Yeah.
I think we're okay. I'm not too worried about you. So we got the friction now. All right. Well, great. Okay. Now let's review some of our other equations. Did anybody have trouble with that? If you're all okay, somebody say, uh-huh.
Uh-huh.
Yeah, I bet you're okay. Okay, well, we had fun. We got the friction. Let me write it over here someplace. It's a keeper. This was the velocity here. That's the velocity. And the friction we think is blah, blah. And I need some room here to do this. Now let's do this. They didn't ask how far down the hill the wheel rolls in 3 seconds. But don't we have kinematic equations for that? Don't we have something like this? The distance something travels is the initial velocity times the time plus 1/2 at squared. Uh-oh, I think I erased my acceleration. Let me put my acceleration back in here just a second now. I think the acceleration, now correct me if I'm wrong, is 3.1392. Hey, can't we find how far it goes down the hill from this equation? See, this is 0. It starts off at 0. I'm going to shut up, and you have a minute, and I want you to find how far it rolls down the hill. Okay, do it. Well, I think I know how far it went down the hill. If I made a mistake on anything, speak up. We needed some thank you points up there on the board. So far, we don't have any thank you points. Braxton, unmute and say hello, Braxton, please.
Hello.
Hey, Braxton, did you get the distance this wheel rolls down the hill? What'd you get?
Yeah, I got 14.13.
That's what I got. I got a distance, you could call it delta x if you wanted to, because we define that as the x direction. I got 14.12, blah, blah. Good going, Braxton. Okay. Well, that was fun. We found out how far it went. Let's ask you some more questions about this automobile wheel rolling down the hill. How about the kinetic energy? Ooh, that'd be interesting. The kinetic energy of the wheel. What is the total kinetic energy of the wheel? Of course, when you start, it's at rest, see? And then you let it go, and it goes faster and faster. And then when after three seconds, I tell you the equation, here's how it works. It's equal to 1/2 IA omega squared. Now do we have IA? Yeah, we have it. Do we have omega? Yeah, hey, we can get the kinetic energy of that wheel. Again, I'll shut up. You find it. You find it and I'll ask somebody for it. Here goes. Well, I got an answer for the total kinetic energy of that automobile wheel after it rolls for 3 seconds. Shane, help us. Unmute and say hello, Shane.
Hello.
Hey, Shane, did you get the total kinetic energy of that tire wheel after 3 seconds?
Yeah.
What'd you get?
I got 623.597.
That's what I got. I got 623. I'm going to round it off to 0.61 maybe. Hey, what are the units on kinetic energy, Shane?
Joules.
You got it. Jolly good show. We have the kinetic energy. Now, did you know that's the total kinetic energy? It's really broken into 2 parts. Let me show you those. Is this going to show up, do you think? Yeah, I think maybe. See, the total kinetic energy consists of the translational kinetic energy plus the rotational kinetic energy. Let's get each one of those. Wouldn't that be fun? Yeah, I think it'd be fun. We're going to get each one. Now this one here is 1/2 the mass times the velocity squared. Well, we got the velocity, we have the mass, it's 9 kilograms. Yeah. Now this one here is 1/2 the Ig omega squared. Do we have the Ig? Yeah, we got. Do we have the omega? Yeah. Hey, look, I want you to find those. I'll shut up. I want you to find the translational kinetic energy and the rotational kinetic energy, and I'll shut up for a minute. Do it. Go for it. Well, here's this is what I'm getting here. But the question is, do they add up to the total? I don't know. Well, let me see. No, I must have done something wrong. Those don't add up to the total. Let me do it again. Something bad happened. Yeah, I think that's probably right. Now, let me see about this one. I wrote down a wrong number here. Now, if you add those up, do you get the total? Do you? Let's see. Well, boy, Jove, if you total those up, and you round it off, you get, forget that one there. I only carried one digit there in the 10th place. Hey, looky here. If you take the translational and add it to the rotational kinetic energies, there they are. There's the translational. There's the rotational. You add them up, you get the total. How about that? It worked. Now, if you got those numbers, say, uh-huh.
Uh-huh.
I need another one.
Uh-huh.
Good. I need one more.
Uh-huh.
I think we're doing okay. We just found, well, we found the translational and the rotational kinetic energies. Now let's do the work. Let's find the work done. I want to find the work done. There's some room right here. What if I ask you, what is the total work done on that automobile tire in 3 seconds? Well, how do you figure work? Does anybody know? How do you figure work? You have to look at the red stuff. Now, you see that normal there? It doesn't do any work. Now, what's really weird is the friction doesn't do any work either. It would if you had relative motion between the wheel and this ramp, this 30-degree ramp here, but there isn't. It's rolling. There is no motion of the wheel relative to the slope. It's rolling. So the friction doesn't do any work. Just because you have a force doesn't mean it does work. Well, the normal's a force, but it doesn't do any work because, see, to do any work, it's got to move in that, what do they call it? Y direction, all right? You could call that the Y direction. Well, it's not the wheel. If that's the Y direction, it doesn't move in that Y direction. The only force that does any work is this 88.29. There's the force, 88.29 newtons. But to do work, you got to take force times the distance. Well, see, the distance is what the distance is 14.1264 meters times the sine of 30. You understand? It goes that distance, but the distance that actually goes down is that distance times the sine of 30. I think that's it, guys. I think this right here is the total work. Multiply all that for me, and let's see what the total work is. Here we go. We're doing the total work of the 88 something newtons there. Well, I got an answer. Did you get 623.6 joules? If you did, say uh-huh.
Uh-huh.
That was Ashley. Ashley, do you recognize this 623.6? We've seen it someplace before. Ashley, where did we see that before?
The same as the total kinetic energy.
That's it. That's it. There's a little room right here. Look here. The sum of all the works done on a body is equal to the change in the kinetic energy of the body. We got a name for that. Ashley, what's the name of that equation?
Work energy theorem.
That's it. That's the work energy theorem. And look, it worked here. Look here. The total work was 623.6. The total kinetic energy was 623.6. How about that? That worked pretty good. Okay. Now, wasn't that fun? That was fun. All right. Well, we know we got all right answers here. We don't really need to check anything, but we're students. We're trying to master this material. And there's some equations we haven't really used yet. There's one that goes like this. The sum of the moments about A is equal to IG alpha plus R cross MAG. Is that my imagination, or did we learn an equation like that? And if we did, we're going to plug it in and see if it works. But if I did that right, that equation has a name. Let me go to one of my excellent students here. Let me pick on Stuart again. I'm always picking on Stuart. Stuart, that equation has a name. Tell the class the name of it. What is the name of it?
Is it the impulse momentum?
No, but I appreciate the try there, Stuart. No, it's not. You want to try again? See, Stuart, to have the impulse momentum, you'd have to have time in there. You'd have to have a T for time. Are you with me? And well, it's different. I can write it for you if you want. Here. Stuart thought maybe it was the impulse momentum. But see, it's different. No, it wasn't. That equation is not the impulse momentum. See, impulse momentum's got a time in it. Stuart, give another guess. What do you think? We're asking Stuart now what the name of this equation is. Stuart, I'll give you a big hint. It's the most important equation in the course. Earth calling Stuart. I haven't lost you, have I, Stuart?
No.
Yeah. Hey, the most important equation in the course is what, Stuart?
Newton's second law?
Yes, it's Newton's second law. This is just a version of Newton's second law. I think I've shown you Newton's second law has different versions. Here, let me write some of them for you. I'll write some of them for you. One of them goes like this.
And then we'll have to go to the doctor. Did you rinse your tub out good?
Ta-da, there you go. And you know, even that one can be written as components. They can be written as components.
But after you were through, you rinsed it all off good?
And you could even do a Z component, but there's also this one. See, this is the translational form of Newton's second law, but there's a rotational form that goes like this. And then there's another one that goes like this. Well, that's the one we just did. That's the one that we wrote down. We're going to plug it in here in a minute. And then there's another one that goes like this. Now, do you see all these equations here? All of these equations are Newton's second law. These are translational versions of Newton's second law, and these are rotational versions of Newton's second law, but they're all Newton's second law. Okay, well, let's plug in this, and then I'm getting tired of this problem. But see, you need to know that. You need to know that Newton's second law is not just F equals ma. All of these are Newton's second law. Okay, let me erase all that. And let's plug in our numbers and see if this will work. Okay, some of the moments about A. Now, what would that be? I think we've done it before. It'll be 88.29 newtons, 0.3 meters, sine of 30 degrees, equals 0.455 alpha, running out of room here, plus the 0.3 times the 9 kilograms times A, which is equal to alpha times 0.3. Now, here's this equation here that I wrote. It's one of the versions of Newton's second law. And really what we're doing here is we're just checking our work. This should work. Solve this equation for alpha, and I'll let you work for a minute on that. Go ahead. I'm going to do the same thing, and if we can get the correct alpha. Did we ever get alpha? Well, go ahead and get it, and then we'll check it. Here goes. Well, I got a value for alpha. I wonder if I did this right. Let me ask somebody here. And I picked on just about everybody today. Here, let me just put I'll tell you what I got. I got 10.464 radians per second squared. If you got that, say, uh-huh.
Uh-huh.
I think that was an uh-huh. I need another uh-huh.
Uh-huh.
I bet that's right. Now we're going to check it. This is called checking your work. It's a foreign concept to a lot of students. See, A is equal to R alpha. So you can get alpha by taking A, which we figured out another way a while ago, and dividing by 0.3. Okay, let's do that and see if we get what we got. Here we go. Well, I'm getting 10.464. Wow, that's what we got. Hey, we checked our work. This Newton's second law business actually works, doesn't it? How about that? It actually works. We checked our work. We got this alpha a totally different way a while ago. And then we got the alpha this way. And we're happy. Well, let's do another problem. Is there any comments or questions on that? Okay, well, if you're happy, I'm happy. Let's do a different problem. Now this is problem just a minute here. Totally organized as always here. This one is 1931. Okay, I'm going to erase this whole thing here unless you have a question, and then we're going to do a different problem. All right, any comment or question? Going. All right, going, gone. Okay, now this problem we're going to work right now is problem 1931. 1931, it is on page 548. Let me find it. Okay, I found it. 1931. Okay, now they have a rod that's 2 meters long. All right. Here's a rod. It's 2 meters long, and it has a mass of 3 kilograms. And it pivots about a smooth pin at A. But down here at B, they have a disc of radius 0.4 meters. A disc of radius 0.4 meters. And there's this little bullet coming in here. There's a little bullet. It has a mass of 0.010 kilograms. And it's traveling 800 meters a second. 800 meters a second. So it's coming in here, and it's, I guess that that disc is made out of wood, and that bullet is going to, what's the word? It's going to stick in. It's going to stick in the wood there. It's going to go in there, embed, I guess is the word. It's going to embed in the wood, and this disc is a 5 kilogram disk. Okay. And then something happens. Immediately after the collision, the pendulum, you could call it a pendulum, I guess, is moving, and it's going to swing up. It's going to swing up to a new position. You know, I'll kind of fake it here. See, it swings up. There you go. It's that kind of makes sense. If the bullet embeds in it and there's a collision, and that happens very fast, and it imparts a velocity. Actually, the bullet is probably in here someplace. Here we'll draw a bullet there. And it's inside that bullet's inside the disc. If it's a wood disc, see there's the bullet there. If it's wood, there's probably a little blue flame licking outside the hole that the bullet went in, because those bullets are real hot. And the hole there is probably charred with charcoal where the bullet went in. And it comes up here and it'll stop. And they want us to find this angle. Okay. Well, there's all the info. What I need here now is I need the moment of inertia about point A for the rod. And then I need the moment of inertia about point A for the disk. And then what we'll do is we'll add those together and get the total moment of inertia. Okay, well, I'll tell you how to do this. It's 1/12 times the mass of the rod times the length of the rod squared. But see, that would just be about the middle. See, the middle of the rod is here. To get it about point A, you'd have to add the 3 kilograms times 1 meter squared. That's for the rod. Now let's do the disc. Now see, the disc is rotating too. It's rotating too, but the equation for a disc is 1/2 mr squared. So you go 1/2 m r, what is the r? 0.4. I don't think I ever wrote that down. Yeah, I did. It's 0.4. I put 4, but it's 0.4. Okay, 1/2 mr squared. But see, that's the moment of inertia if it was just spinning about its center. It's not. It's rotating about A, so you have to add to it the 5 kilograms. See, here's the center of the disc, and this distance from here to A is 2.4. Okay, I want you to add all of that and add all of that and give me the moment, the total moment of inertia about point A. And I will shut up and let you work. And then we'll figure out the problem. Go for it. If you have any questions, just speak up. Well, I got a total moment of inertia about point A for this whole pendulum thing. And I wonder if that's what you got. I wonder if I lost. Hey, Taylor, are you still with us? Earth calling Taylor. Uh-oh. I think we've lost Taylor. Shane, you won't let me down. Shane, unmute and say hi, Shane, please.
Hi.
What'd you get for the total moment of inertia about that smooth pin there at 8?
I got 33.2 kilograms meter squared.
That's what I got. I got 33.2 kilogram meter squared. Good going. Excellent. Okay, now what we need to know now is during the collision. Now the collision takes place very fast, a tiny fraction of a second. But during the collision, you have a force of the bullet acting on the disc. Here, I'll draw it for you. It starts off here, but it starts to penetrate, and that force starts to move inside. You understand? But the bullet is putting a force on the disc going to the right. But did you know the disc is putting a force on the bullet? When it first starts here, the force is like that, and as the bullet slows down, I think the force gets smaller until it stops. But you know what? At any instant during that collision, and that collision takes place in a tiny fraction of a second, but at any part of that collision, the forces will be equal because of Newton's third law. Newton says for every action, there's an equal and opposite reaction. So the forces will cancel out. And so what you have is I was going to say you have conservation of linear momentum. And you would if this disk was all the mass that we're talking about. But we also have this mass there. And what you have to use on this problem is the conservation of angular momentum. See, angular momentum is different for particles and for bodies. I think I skipped over this, but now's a good time to tell you about it. Angular momentum, the book uses an H. And what angular momentum is for particles, it's the first moment of linear momentum. See, this here is linear momentum, but angular momentum is, well, in this case, it would be 2.4. It would be 2.4 meters times the mass of the bullet, which is 0.010 kilogram, times the velocity of the bullet, which is 800 meters a second. That's the angular momentum. They use a symbol H for angular momentum in this book. But I have told you about the angular momentum of bodies. And it's equal to I omega. And we've got the I, it's 33.2. It's 33.2 kilogram meter squared. Now the omega we don't know. However, we have a relationship at the end of the collision. The velocity of that body with the embedded bullet is equal to r omega. So now wait a minute. This is the initial angular momentum. It also has a final angular momentum. I know this is a little confusing. I need some room to write the equation. How are we doing? Oh, gee, we only have 5 minutes left to work on this problem. Have you ever noticed when you're having fun how fast time goes? But here's the plan. We're going to write the conservation of angular momentum because the distance r for the bullet coming in is from here to here during the collision, and the distance r for the disk and the, wait a minute, I'm getting confused now, just a minute. Okay, now here's the plan. There are no external forces, just internal forces of the bullet acting on the disc and the disc acting on the bullet. They cancel out. The forces cancel out, and their moments cancel out. See, moments are forces times distance. Well, that force is at that same distance for the disc as that force at the same distance for the bullet. They're opposite directions on the forces, but they have the same distance, therefore they have the same moment. So the sum of the moments is 0. Here's the equation. Oh, gee. I'm not going to make it, am I? I might get so far as to write your equation for you. The sum of the moments about A is equal to we need the bullet and the disc. We need the angular momentum of the bullet final, and the angular momentum that's at the end of the collision. See, they're moving, and this is the angular momentum of the disc times I need the time in here, minus the initial angular momentum of the bullet, which is, this is the initial, this is the final at the end of the collision. The R's we know, the mass of the bullet we know, the moment of inertia of the pendulum we know. And here's the beauty. This is going to be 0 because the sum of all the external moments acting on the pendulum during the collision is 0 because the forces cancel out. So what we have here is all of this is equal to 0. And my time is up. I didn't get done. It's a pity. Hey, I could finish this next time. You might try it. You might try it and see if you can solve it. And we'll try to finish it next time if I can remember. It's sad, but the time has come to an end. Do you have any last comments or questions? Okay. Well, bye-bye, students. I'll see you. Hey, there's no class on Wednesday. And did you know that? I won't see you again till 9:30 next Monday. And that's the last week of school. But hopefully we'll all be okay and meet then. Okay, goodbye, bye. Bye-bye now.
Bye.
Bye.
Hasta luego.